Hello and welcome to this video on the implementation of an algorithm to find the maximum number of toys that can be purchased within a given budget, while also taking into account that some toys may be defective. In this video, we will be using a combination of sorting, binary search, and an ordered underscore set to solve this problem. The maximum toys function starts by creating a new vector called v, which contains the price and index of each toy in the input array A as a pair. This vector is then sorted in ascending order by price. Next, the function creates a new vector called prism. This vector is used to store the cumulative sum of the prices of the toys in the v vector. This will be used later in the algorithm to perform binary search. The function then enters a for loop to iterate through the queries to d vector. For each query, the function calculates the maximum number of toys that can be purchased by using the following process. Step 1. Initialize an integer variable called money, which is set to the budget for the current query. This line of code is checking if the budget for the current query is less than the price of the cheapest toy. If this is true, it means that it is impossible to purchase any toys within the given budget, so the function pushes 0 into the ans vector and continues to the next query. This check is a simple but important optimization to ensure that the function doesn't waste time trying to find a solution when one is not possible. Step 2. Perform binary search on the prism vector to find the largest index I such that prism I is less than or equal to the budget. This if-else condition is used to determine how many toys can be purchased given the budget. The variable CT is used to keep track of the number of toys that can be purchased. The first if statement is checking if the cumulative sum of prices at index is equal to the budget. If this is true, it means that all toys up to and including index can be purchased, and the number of toys that can be purchased is index plus 1. The money variable is also set to 0 as all the budget is used up. The else statement is executed when the cumulative sum of prices at index is not equal to the budget. In this case, the budget minus the cumulative sum of prices at index 1 is calculated, and the money variable is updated. The CT is set to the index, and index is decremented by 1. This is because the cumulative sum of prices at index 1 represents the total cost of all toys up to but not including index, and by subtracting this from the budget, we can find out how much money is left over to spend on toys at or after index. Step 3. Initialize an unordered set called defective. This set will be used to keep track of the defective toys for the current query. Step 4. Iterate through the defective toys for the current query and adjust the money and count of non-defective toys that can be purchased. This for loop is used to remove the defective toys from the list of toys that can be purchased. The loop is iterating through the defective toys starting from the second element of the query vector, which is the number of defective toys. For each defective toy, the index of the toy in the original list of toys, A, is calculated by subtracting 1 from the value in the query vector. The if statement is checking if the price of the defective toy is less than the price of the next available toy in the sorted list of toys, V. If this is true, the price of the defective toy is added to the budget, and the count of toys that can be purchased is decremented. The else if statement is checking if the price of the defective toy is equal to the price of the next available toy in the sorted list of toys, V, and if the index of the defective toy is less than or equal to the index of the next available toy. If both conditions are true, the price of the defective toy is added to the budget, and the count of toys that can be purchased is decremented. Finally, the defective toys index is added to the defective set, so it will be skipped when the while loop iterates through the remaining toys. This means that defective toys will not be considered when finding the maximum number of toys that can be purchased. Step 5. Iterate through the non-defective toys and purchase as many as possible while still staying within the budget, taking into account the defective toys. This block of code is used to calculate the maximum number of toys that can be purchased with the remaining budget. The while loop is iterating through the remaining toys in the sorted list of toys, starting from the next available toy after the defective toys have been removed. The loop is running as long as the current index is less than the total number of toys and the remaining budget is greater than or equal to the price of the current toy. For each toy, the if statement is checking if the toy's index is present in the defective set. If it is not present, it means that the toy is not defective, and it can be purchased. In that case, the price of the toy is subtracted from the remaining budget, and the count of toys that can be purchased is incremented. Finally, the index of the current toy is incremented and the loop continues till the end. After the while loop, the final count of toys that can be purchased is pushed back to the answer vector, and the max, 0, CT is returned. This is done to ensure that if the count of toys is negative, the final value returned will be 0. And that's it. With this implementation, you can find the maximum number of toys that can be purchased within a given budget, while also taking into account that some toys may be defective for multiple queries without the need of calling extra function. Thank you for watching, and I hope this video was helpful.